Hey Andy, thank you for reaching out. I decided to record a video to demonstrate some of the functionalities that I've implemented in my research or prototype spreadsheet environment called Minicell. My work right now is focused on providing approachable graph modeling for non-programmers. Just like the Calc Intelligence project at MSR, Minicell aims to extend the range of applications that can be tackled with the spreadsheets without loss to usability and accessibility to non-experts. In our case, the task that we're trying to tackle and make easy for non-programmers is common graph modeling tasks. Let me give you an example. I live in Davis, and I have friends who live in Sacramento, which is only 20 minutes from Davis, and Berkeley, which is only 90 minutes from Davis if you take the shuttle. I also have friends who live in Portland, and normally when I want to go to Oakland, I take the shuttle to Berkeley and then go to Oakland. So if I wanted to add Oakland here, or maybe I want to add Oakland here, and I know from Berkeley to Oakland you can conveniently get there with BART, so let's just say it only takes 20 minutes to get there. So what's happening here is that, as you can see, spreadsheets are pretty powerful in encoding this particular representation of graphs. In this case, this is an adjacency matrix. But what happens is that spreadsheets do not provide any means for us to treat this range or treat this piece of data as a graph. And by that I mean there's no way in the spreadsheets, apart from integer linear programming and esoteric approaches like that, to, for example, calculate the shortest path from Portland to Berkeley, or that there is no convenient way to calculate the max flow of this graph, or really work with this graph in any capacity. We can only deal with this information as a table inside the spreadsheet environment. Minicell aims to solve that without any need to pull this data into a high-level programming language like R or Python. Minicell allows you to turn this data into a graph and work with it as a graph value. All you need to do is to use the extract formula and pass a range to the extract formula, like A2 to maybe G10. And Minicell would extract a dynamic graph for you and would store it in the cell A1. This is a graph. Right now, Portland is not connected to any place. So let's say from Portland to Davis, maybe we could get there in 360 minutes. That's about 6 hours. So note that my graph is dynamically updated as I change the underlying range, the values in the underlying range. Not only Minicell adds first-class support for graphs as a possible value for the data types, it also augments the formula set of the spreadsheet environment with formulas to work with graph values. So in this case, if I want to find the shortest path between Portland to Oakland, all I need to type is the shortest path formula, give the graph as its first argument, and give the source and the destination as the second and third arguments. In this case, I want A5 and E2 to be my source and destination. Minicell calculates the number 470 for the shortest path between Portland to Oakland, which seems right. Now suppose there was a super fast highway built between Sacramento and Oakland that would get you from Sacramento to Oakland in 10 minutes. Would that affect the shortest path from Portland to Oakland? Let's see. Sacramento to Oakland. Sacramento, Oakland. Let's just say we get there in 10 minutes. Note that not only the graph changes, but also the shortest path value changes immediately as the changes are propagated. Here's a set of operations that I intended for Minicell support for graphs. You can see operations for calculating the union of graphs, minus of graphs, certain things for filtering, certain things for matching, reversing the edges, and common things that you would expect. I haven't really fixed these, and I haven't really implemented all of them in Minicell. These are subject to change, but this is a rough sketch of the graph operations table. I also experimented a little bit with temporal values and shapes in Minicell. These are not part of my research, but it's some Christmas hacking, so I thought I would share this with you. Over the weekend, I used Haskell's awesome diagrams library to add some basic functions and data types for cells that would support shapes. So let's give it an example. Suppose I want to have a circle inside a spreadsheet cell. All I need to do is to have the shape formula and have it on B1. And this would give me a circle. I could have a triangle, or I could have a square too, but let's just stick with the circle. I can paint the shape that is stored in A1 using a color. Well, let's give it a color first. Let's say green. And let's say I want to paint this with the color that is stored in cell 2. If I wanted to make it red, I could make it red, or if I want to make it cyan. And I can also concatenate these two shapes vertically. Let me get another circle. So let's say color A1 with the color red this time. Color A1 with B3. Oh, I think the actual function is paint. A1 with B3. So now I can use Minicell primitives to combine these shapes. For example, in this case I want to concat these two shapes horizontally. So I use the hconcat formula. And there's our result. Note that if I change the colors, you get an immediate visual feedback, and this change is propagated all the way down to all the cells and formulas that are using A2 or A3 as a value. Another idea I started experimenting with was having values that flow in time. In particular, I experimented with having integer values that flow in time. For example, the number of seconds that has been passed since Unix epoch. If I have a formula like this, let's do some arithmetic with this value. For example, let's say, what is C4 mod 5? Each time I get 0, 1, 2, 3, 4, and back to 0 again. So I can use this value to make a 5-frame animation. Let's see how this works. I'm interested in rotating the shape that is stored in A2 based on the parameter that is specified in D4. To do that, all I need to do is to type turn the shape that is in E2 based on the value that is in D4, and the cycle is 5. So now you see this shape rotating each second as time goes by. So now not only I have the Unix timestamp here as a value that flows in time, but also I have the value in D4, and also I have this shape value that flows in time. obviously all the natural things that you would expect from the spreadsheet environment would carry over to this domain as well. So if I change this color to yellow, I would get a yellow animation, and if I change this color to maybe green, I would get a green animation. So that's all I have for now, Andy. These were some of the features that I've implemented in Minicell spreadsheet environment. I'm looking forward to chat with you or any other member of the Calc Intelligence team about any matters related to the spreadsheets. As for technical details, Minicell is mainly implemented in Elm and Haskell, half in Elm and half in Haskell. I use Elm for the front end, and Haskell does all the heavy lifting for various sorts of parsings, I/O, and graph computation, which I use FGL for that purpose. This was Nima, and this was an introduction to the Minicell graph processing environment. Thank you for your time and attention.